Right, it's 8:30. Let's go and get started this morning. Good morning, everybody. How's everyone doing today? Doing all right. Last day before spring break, so I know everyone's excited. It's probably bad. Actually, the spring is not so bad, but in the fall, the last class before Thanksgiving, I think is always the least attended class every semester. So spring break comes close, but it's not as bad. Happy to see all of you guys today. So it's good. I'm really thankful that you're here. I was telling my class yesterday that I'm contractually obligated to be here. And so whether one person shows up or the whole class shows up, I have to be here. So it's always nice having people here with me at least pretend to listen to what I'm saying each day. So thank you guys for coming. Okay, so the plan for today is we're going to be finishing up our lecture notes on integral calculus. We have one main thing left, and that's the divergence theorem. And so I want to make sure we go over that. And then we're going to move on to the next thing. And so the next thing is Fourier. And so today's going to be a little bit of a transition day. And so we'll probably spend the first half finishing up the divergence theorem. And then second half, we'll kind of start. It's a little bit, it is a little bit strange to kind of start something new today, just because we're about to take off for a week. But I at least want to kind of introduce the concept to you guys. So that when we come back from spring break, hit the ground running. All right. And so remember, some announcements. Remember, homework 4 is due this Sunday, so make sure you get that in, and make sure you take the mid-semester check-in survey as well. So I just checked it yesterday morning, and I think maybe only about a third of the class has completed that. So please make sure you do it. It is a required survey. It should only take you about 5 minutes, even less if you don't do the free response at the end. And so please make sure you fill it out. It is, basically free homework points. So, please do it when you do it. I'll send an announcement reminding everyone about the survey today as well. So please make sure you do it. Okay, so that's all my announcements. Are there any questions I can answer before we get started for today? Okay. All right, so let's go ahead and get started. All right. And so where we're going to start today is something called divergence. Okay. So last time when we met up on Tuesday, we spent the last half of the class talking about surface integrals. Okay? So let me review what the surface integral represents. Okay. Surface integrals are a very important part of engineering physics, because what they represent is this concept called flux. So flux is something that is it comes up a lot in engineering physics. Definitely a lot more so in thermofluids. And so if you talk about if you're specialize in fluid mechanics or heat transfer, flux is something that you're going to become very familiar with. And the idea behind flux is that it represents the transport of a certain quantity that passes through a surface. And so I believe last time we did an example from fluid mechanics, which is mass flux, right? And so whenever you have a flowing fluid, and so let's say you have a fluid that's flowing in a pipe, or maybe like the air that's coming through your air conditioner, you're interested in seeing how much mass or how much quantity of that fluid is passing through certain surface. If we have, some kind of surface here. And then we have fluid that's kind of passing through. And so when we compute the surface integral, the surface integral basically computes how much of that is going, right? So when you evaluate that surface integral, it'll give you something like the mass flow rate. So that's great. And so you'll see this concept show up in a lot of engineering physics, particularly, like I said, fluid mechanics and heat transfer, especially if you take the more advanced classes. The problem with the surface integral is that it is a pain in the ass to compute. Right? Surface integrals is probably one of the least fun things to compute in calculus, right? It becomes a little bit easier once you get kind of good at coding. And so if you come up with ways that like MATLAB or Python coding, it becomes a little bit easier to compute it in there. But it's still kind of a pain to compute. Okay? What we would rather do, and what's a lot easier, is to a lot of times we like to convert, or we would want to convert the surface integral into a triple integral. And believe it or not, that's actually going to be easier for us to compute. But I kind of spoiled the what divergence theorem is here. So divergence theorem is basically what allows us to do this. So it basically lets us take a surface integral and convert it to a triple integral, as long as we make kind of one small change to the integral. Okay. Let me list out what the let's write down what the divergence theorem is mathematically. And so first, let's define some definitions. So let's say we have a region T. So we're going to have T represent a closed bounded region in 3D space. And then this T is bounded by a surface S. So S is basically just the exterior of T. So it's kind of like a shell, right? The analogy that I always like to think about when you're talking about bounding surfaces, if you think of like an ice cream bar, and so if you ever had those ice creams on a stick where it's like vanilla ice cream on the inside and has that thin chocolate shell on the outside. So the vanilla ice cream here would be T, and then the chocolate shell would be S. Okay, so that's kind of what I think about. Okay, so now that we have T and S, let's go ahead and define the mathematical form for divergence. And so on the one hand, on the one side of the equal sign, we have a triple integral over the region T of the divergence of F. And then on the other side, we have a surface integral, which is a closed surface integral. So I'm going to use this kind of circular notation here on the region S. The vector field dotted with n. And of course, one thing that we need here is some vector field. Let me write here F is a so let's write down in words what each side of this equal sign represents. So on the left hand side here we have a triple integral. Over the volume T. And the integrand here is going to be the divergence of F. And on the right hand side here, we have a surface integral over the bounding surface S. Of the vector field F. And of course, just like we talked about earlier, the surface integral represents how the flux of F through the surface S. And so what the divergence theorem says is that these two quantities or these two integrals are equal to each other. Okay. And the important consequence of this is that, if you have one integral on one side, so let's say that, you have a mathematical equation, or you have an engineering equation that has, a surface integral in it, right? Instead of computing that surface integral, what you can do instead is you can replace it with this triple integral and compute that instead. Okay. And we'll do a couple examples of that so you can see that. Right. So, you're probably thinking, how is it possible that a triple integral is easier to compute than a surface integral, right? Triple integral has three integrals, right? So how can that be easier than two integrals? Well, when you do surface integrals, if you remember from last time, you have to spend a lot of time, parameterizing your surface, doing kind of basically replacement of variables, and then plugging in for that, and then, doing a bunch of extra stuff. So, a lot of times the surface integral ends up being more annoying to compute because of that parameterization step. Okay. You'll see that in the next example. Okay. Any questions on this? Okay. All right. So let's do an example to kind of show you how it works out. All right, so let's go. This example we're going to verify divergence theorem. So we're not going to prove it, but we're just going to do an example just to show you that it actually does. Okay. So first thing we need a vector field. So let's say our vector field F is going to be given by 7x, 0, and minus z. Okay. And our domain will be a sphere of radius 2. And we're going to center it on the origin. So the equation for the sphere is going to be x squared plus y squared plus z squared. All right, so what we're going to do is we're actually going to compute both sides of the divergence theorem. So we're going to compute the surface integral and we're going to compute the triple integral. And I'm going to show you that we're going to get the exact same thing. So that shows you that divergence theorem is real. It's actually legit. Okay. So let's start with the surface integral. Kind of a side objective of this example here is to show you, just how annoying it is to compute surface integrals. Okay. All right. And so if you remember from Tuesday, when we compute surface integrals, we need to compute the surface normal and we need to parameterize the surface. And so luckily, we're working with a sphere here. And so we talked about the parameterization of a sphere last time. So for a sphere, check notes from last time. And so for a sphere, our surface is given by R. Remember, function R is a function of u and v. So remember, for surfaces, we need two variables. This is equal to. And keeping in mind that we have a radius of 2 for this sphere, so it's going to be 2 cosine of v sine of u. 2 cosine v sine of u. 2 So we're fortunate in this case, well, fortunate and unfortunate, that we already, went over the parameterization of a sphere. And so, you don't have to go through that. The unfortunate thing is that this parameterization is not the easiest to work with because we have a lot of sines and cosines in there. Because the next thing we're going to do is we're going to compute the surface normal, right? And so in order to do that, we need to take the derivatives of this. So we're going to need to do partial r, partial u, and partial r, partial v. Okay. Remember what these derivatives represent. These derivatives represent vectors that are tangent or parallel to the surface. Okay. All right. So if we compute these, we get -2 v sine u. 2 cosine v cosine u. And 0. That's partial r, partial u. And then partial r, partial v. We have -2 sine v u. -2 sine v sine u. 2 sine. So we've taken our parameterized surface, we've taken these derivatives, and so now we have the two tangent vectors in the plane. And so to get the normal vector, we just have to take the cross product between these two vectors. Tangent vectors, take cross product. So we're going to take their cross products to compute the normal vector. So normal vector is equal to partial R U cross product with partial R E. Okay. So again, I'm going to skip the details of this cross product just for kind of time's sake. I want to make sure we get through everything today. But definitely, go back in your notes and check. When you're doing the homework and stuff, check and make sure that this is actually valid. All right. So what we get from this is work cosine squared B cosine U or cosine squared B sine U, and then 4 sine B sine . So that's one piece of the puzzle, right? So for the surface integral, first thing that we need is the normal vector, which is what we have here. The next thing we need to do is we need to put our f in terms of our parameterization. Okay. Any questions on this so far? Okay. All right, so let's go on to the next step. And so we're going to do basically a substitution. And so we're going to take our vector field and then put it in terms of U and V based on the parameterization of our surface. Okay, so let me write down F again. So F equal to 7x 0 Z. Okay. And let me write down our parameterization again. So our parameterization is R U and V is equal to 2 cosine V so U 2 cosine V sine U 2 sine. Remember what this parameterization represents, right? So we have 3 components of this parameterization. And so the first component is going to be x of U and V. Second component is y of U and V. Third component here is Z, U and N. Okay. And if you look at our vector field here, our vector field is given in terms of x, y, and z. So there's no y there, of course, and so it's just x and z. And so when I say that we need to put f in terms of u and v, we're basically going to be taking these expressions from our parameterization and plugging them in to the particular values there. Okay. All right, and so if we do that, our f first we have 7x. And so in for x, I'm going to plug in our x of u and v from our parameterization. So it's going to be 7 times 2 sine of v cosine. Our next component of f is just 0. And so 0 is just 0. We don't need to plug in anything for that. And then we have minus z. And so we're going to plug in our parameterization for z. So this is going to be a minus 2 sine and of course, for the first term, you could simplify that a bit. So 7 times 2 is 14. So you can just replace that with 14. A little bit, just so you can see both. And so now we have both components that we need. So we have the normal vector. And so the normal vector is kind of what we saw for in the previous step. Now we have f of u and v as well. Okay. So now we're going to take their dot product. Because that's what's the integrand of the surface. And so we're going to take the dot product between these two vectors, and so we have that product with the normal vector. Okay. So let me go ahead and do that. And so we have we're going to multiply the first components, and so we have 14 sine of v, sine of u, multiplied by the first component of the normal vectors. We have 4 cosine squared of v sine u. Okay. After that, we have the multiplication of the second components. And so obviously the normal vector here has a second component that's non-zero, but our f here, our second component is just 0. And so I'm just going to say, 0 times anything is still 0. Right? 0 is that one unbeatable boss in math. And so, no combination of sine and cosines can overcome 0. And then we have the z components. Okay, the z components, we have a -2 sine v. That comes from our f. And then from our normal vector, we have 4 cosine v sine v. Well, there's a lot of arithmetic here, and so make sure you're careful in doing all the multiplications. Make sure all the sines and cosines are accounted for. Okay. And so when you do this, you get 56 cosine cubed here for v. V sine squared u minus 8 cosine v sine squared right. So that's the result of the dot product. So now that we've computed the dot product, we are ready to compute the surface integral, because that dot product is our integrand for the surface integral. Okay. And so our surface integral, remember, is like this. And so if we plug in for this, we have double integral of 56 cosine cubed of v cosine squared of u minus 8 cosine v sine squared of v. Okay. There you go, du dv Right, we need to set some bounds on these integrations, and so these I'm just going to give to you. And so you're just gonna have to trust me on these ones. But our U and V here, in spherical coordinates, those represent kind of the angles of our sphere, right? And so over the integral U, we're going to integrate from 0 to 2 pi. And then over our V variable, we're going to go from minus pi over 2 to pi over 2. Okay. Right, and so if you're familiar with spherical coordinates, our variable U here, that's our polar angle. And then our angle, so that's the one that kind of goes in the XY plane. So that's why we're making a full rotation on that one. And then our variable V, that's our azimuthal angle. So that goes from kind of the Z axis. Yeah. Okay. And so if you do both, then you kind of sweep over the entire sphere. Okay. And so this is another part where you're going to have to trust me because I do not want to do that big ass trig integral there. And so, of course, actually performing this integral, you need to do a lot of trig identities, probably a lot of crying along the way, but eventually you'll get it done. Or if you do it the easier way, you can ask Wolfram Alpha, or maybe ChatGPT. ChatGPT might be able to do that integral. So try it out sometime. But if you evaluate that integral, so luckily for you, I made these notes before ChatGPT was a thing. So I did all the crying for you, so don't worry about that. And so this integral here is equal to 64. Okay. So after lots of so it's a little bit of a disappointing result. So we did all this work to set up the integral, and then we don't actually do the integral. Okay, but you can kind of see why surface integrals are such a pain. So we did all that work just to set up the integral, and then we didn't even do the integral itself. So the integral itself is probably going to take us another 30 minutes. So that's kind of why I kind of shied away from it. But the result of this is 64. Okay. Any questions on this? Yeah.
So when we were finding the normal vector, we did the partial of r with respect to u cross with the partial r with respect to v. If we switch that, would it give us like a different answer?
It would make the answer negative because the reason we do partial r partial u first is because we want the normally pointing out from the plane. Okay. And so if you reverse it, then it would point into the plane.
So always do u cross with v.
Exactly. Yeah. That's just the convention that's established. Okay. Yeah. Right, any other questions on this here? Okay, all right, so believe it or not, that was the hard part. So now let's go ahead and do the easy part. Okay, so now let's do the triple integral side of the divergence. And so our triple integral side looks like this. Triple integral of this quantity here. Okay. And so let's go ahead and write out the divergence. And so if you remember from a couple of weeks ago, when we take the divergence of a vector field, it looks like this. Partial F1, partial X plus partial F2, partial Y. Actually, these aren't vectors. I don't know. Plus partial F3, partial. Okay. So F1, F2, F3 here, those are the components of our vector field. Okay. So let me go ahead and write down FC again here, just to remind you. So F in this problem, 7x, 0 minus z. Okay. So let's go ahead and compute the divergence. And so the divergence in this case, we're going to have partial x of 7x plus partial y, 0 plus partial z of minus. So this ends up being pretty nice, and so it's a very nice expression here. So you know, partial x of 7x, that's just going to give us our constant 7. Partial y of 0 is just 0. And then we have partial z of minus z, and so that's going to be a minus. Okay. Right, and so we plug all this in, we just do the arithmetic, we have 7 minus 1, which is 6. Okay. And so our triple integral of the divergence of f dv is just going to end up being the triple integral 6. All right, so I'll come a little clean with you guys. So I picked this example on purpose because I knew the divergence would be very easy to compute, and the surface integral would be very much a pain to compute. So you know, most problems are not going to be this. You're not going to see this much a difference between the surface integral and the triple integral. But you know, in general, you know, the triple integral is going to be easier. Maybe not this much easier, but you know, easier in general. Okay, and so this is really nice here because we have just a constant. And so we can just pull that constant out in front. Okay, so we have a 6 triple integral of nothing. Okay, or it's not nothing, there's a 1 there. Okay. And this part's nice right here because we don't actually have to integrate anything. Because we know that when we have kind of a blank triple integral like this, right, when there's nothing, you know, there's just a 1 on the integrand, this represents just the volume of our domain. All right, and so we know our domain. Our domain here is just the sphere of radius 2. And so the volume of a sphere, we know it's 4/3 pi r cubed. And so if we know our radius is 2, we can do 4/3 times pi 2 cubed, which is 8. And what we get for the volume is 32/3. All right. And so let's go ahead and plug that in. And so our triple integral now triple integral of the divergence of V, or divergence of F, excuse me. So this can be 6 times our volume, which is 32/3 pi. Okay. Let's go ahead and cancel this. And so we have a 3 that's going to cancel out with the 6. And so that's going to be a 2. So what we get from this is 64 pi. Right. And so voila, you know, if you look at the result from a triple integral versus the surface integral, they give you the exact same thing. And the surface integral, we didn't even do all the work for that. And so, you know, it's you can see here that a lot of times this triple integral is going to be a lot easier. Okay. Of course, you know, I did pick this example just to make it seem like it's a lot better than it actually is, but you know, that's kind of what everyone does nowadays. If you look at our university officials, you know, they always pick data, they always pick stories to fit their narrative. So it's kind of the same thing. All right, any questions on this example here? Okay. All right, let's do one more example where I'll show you, you know, another example here where it's going to be easy. Okay, so let's use the divergence theorem and let's use it to evaluate the surface integral. And so we have a surface integral S of x cubed dy dz plus x squared y x plus x squared z dx y. And our surface S is going to be a cylinder of radius A with a height of B. So it looks like we have our cylinder. Cylinder has radius A. Height of the cylinder is all right, and so this problem is asking us to compute the surface integral. Okay. All right. So hopefully, one thing that you'll get from today is that computing surface integrals is a big pain in the butt. Okay? And so we're not going to do that surface integral. What we're going to do is we're going to use divergence theorem. Let's convert this into a triple integral and let's compute that instead. All right, so first thing we need to do is we need to look at our surface integral and we need to extract our vector. Okay. So this part is probably the only really new thing about this. And so if you remember, our usual form for the surface integral looks like the form. So surface integral is normally a dot product f and n. Okay. So of course, we don't really have it in this form in this problem. But what we can do is we can kind of extrapolate certain parts to be from that. Okay. In particular, right? We know that the dot product is going to involve, three components because we're in 3D space, right? So we have kind of the x components multiplied by each other, plus the y components multiplied by each other, plus the z components multiplied by each other. Okay. If you look at our integrand here, we have kind of that same form. So this right here and these two right here, okay. You can see that these three, you can kind of look at the evidence here and kind of look at that these three components come from that dot product. And so this would be kind of our x component, this is our y component, and z. Okay. And so because of this, we can kind of extrapolate that our vector field F is going to be those three components minus the integration variables, right? So all the dy, dz, dx are not going to include this. Okay. And so our f in this case is going to be x cubed, which is the first component there, x squared y, and x squared z. Okay. And so those three came straight from the difference. Okay. Any questions on how we extracted f, our vector field from that integral there? All right. So now that we have the vector field, let's go ahead and plug this into divergence theorem. So according to divergence theorem, our surface integral is going to be equal to a triple integral of the divergence of f. And so our next step is going to be to compute the divergence of f. Okay, so we have f here. So let's go ahead and take it to divergence. And so the divergence of f partial x cubed plus partial y x squared y plus partial z x squared z. Okay. And so if we evaluate those partial derivatives, we get 3x squared plus x squared plus x squared. And so we're going to get 5x squared. Okay. And so our triple integral, the one that we have to compute here, is 5x squared. Actually, let me go ahead and plug in for dv. So dv here, dv is going to be dx dy c. Okay. Right, so we're in pretty good shape here, and so we went from that kind of very complicated surface integral to something here that looks a lot more manageable. Okay. The issue here now is comes in the bounds of the integration, right? And so our bounds they're going to be basically determined by our domain. Okay. The issue here is that our domain here is a cylinder. And so since our integration domain is a cylinder, we need to convert this integral here into cylindrical coordinates. And so we're going to do a change of variables. And so Conversion from Cartesian to cylindrical coordinates, we're going to have x is equal to r cosine theta, I is equal to r sine theta. Okay. That's the main thing, but we also have to convert our integrand as well. Okay. And so in Cartesian coordinates, we have just dx, dy, dz, but in cylindrical coordinates, we have r, dr, d theta. So let's go ahead and plug these in. And so if we plug these in, we have our triple integral. And I'm going to leave space here because we're going to put the bounds on these integrals very soon. 5x squared, so that's going to be 5 r squared cosine squared of theta, okay, times r dr d theta. Okay. We're getting close. So we're almost at a point where we can evaluate this integral. The last thing we need here is just the integration bounds. Okay. Okay. And so this first integral here, or I should say the innermost integral, this is going to be our integration bounds on R. And so R being the radius of our cylinder, okay? And so if you go back to the problem statement, we know that our cylinder here has a radius of A. And so our integration bounds in R is going to be 0 to A. So that's the innermost integral. Middle integral here. Because the d theta is the second integration variable that we have in our stem there, it's going to be our integration bounds on theta. So theta is easy because we're doing a full rotation of the cylinder, so we're going all the way around. So our integration bounds in theta are 0 to 2 pi. And then finally, the outermost integral, this is going to be your integration bounds on z. And so we know our cylinder has a height of b. And so our integration bounds there are going to be 0 to b. All right. So now that we have our integrand here, we have all our integration bounds. Now all that's left is just to perform this integral. So this integral here is a lot more reasonable. And so it's definitely not as hectic as the previous ones that we've done, because we basically have 5r cubed times cosine squared of theta. Okay. Okay. But again, in the interest of time, I want to make sure I get to the physical interpretation of divergence theorem. I'll let you guys go ahead and verify this yourself. Okay. And so this integral here is going to be 5 pi a to the 4th b divided by so that was a lot easier than if we tried to do the surface integral. Okay. If we try to do the surface integral, we still have to convert to cylindrical coordinates, but then we'd have to deal with parameterizing the surface, plugging in for the parameterization, computing the normal vector, and this surface is not, there's sharp corners on the cylinder, and so you'd have to do the sides of the cylinder and the top and bottom of the cylinder separately. It becomes a big pain in the butt. Okay. And so if you can convert your surface integrals to triple integrals, most of the time it's going to save you work. It's going to save you money. All right, any questions on this? Okay, all right, so last thing I want to do today, we didn't end up getting to Fourier, but that's okay. We'll start something new after the spring break. I want to talk about the physical interpretation of the divergence. So just like we did for Green's theorem, we're going to look at both sides of the divergence theorem, and we're going to talk about what each side physically represents. All right. All right, so there's our divergence theorem. I'm going to start with the right side because we've kind of been talking about the surface integral kind of a bit already. Okay. And so we know, is based on our physical interpretation of the surface integral, that it represents a flux. Okay. So this represents flux field It represents the flux of the vector field F through the closed surface S. Okay. And the closed thing there is important to highlight. So that's why I kind of underlined it. Okay. Because remember, in divergence theorem, the surface that we compute the surface integral on is quite unique, right? It's unique in that it's actually the bounding surface for our region V. Okay. And so that means it's a closed surface. So it's like the closed chocolate shell around an ice cream ball. Shouldn't be for breakfast. Okay. So that's important. And so, because we talked about, the surface integral being, a flux, but its interpretation becomes a little bit different when you have a closed surface. So let me kind of show you what I mean. All right. And so let's say that we have a surface. So let me go ahead and draw a sphere, this easiest three-dimensional object to draw. And let me draw some vector lines that go through this sphere. So let's say we have a vector field. So let's say that we have a field connected. Okay. So S here, S is a closed surface. And so based on this, just based on this image, we're not going to do any math at all. I can tell you, what the surface integral or what the flux of this vector field F through this surface is going to be. So of course, these purple lines here represent F. Okay. And so if you look at something like this, like you'll probably say that you'll probably kind of your first intuition might be, we have these vector lines, they're passing through our surface. And so our surface integral should give us something that's non-zero, right? Because we have vector field arrows passing through the surface. Okay. What I would tell you is that most likely in this situation, because the surface is closed, our surface integral, our flux, our total flux is going to be close to zero, if not zero. So that might be a very jarring point, right? Because we've talked about, if you have vector lines passing through a surface, that's what the flux represents. So how can we have vector lines passing through a surface, and how can I be telling you that this is zero? Okay. Let me show you why. The key to this whole thing is kind of how we interpret the surface normal. Okay. And so if we look at a point that's kind of on the top right of this cylinder, the surface normal points in that direction. Okay. But if I drew the surface normal at a different location on the sphere, so let's say I drew it on the bottom left of the sphere, it would go in the opposite direction. And so what we have here is that we have situations where, yes, on subparts, on certain regions of the surface, our surface integral is going to be non-zero. Okay. But when you take the surface integral over the entire surface, there are going to be parts where the surface integrals are going to cancel out. Okay. In other words, to kind of put it in even more plain language, okay, on this region up here, we use green for this. On this region right here, what we can say is that the vector field F is going out of the surface. Okay. Whereas on the other part of the surface here, we have vector lines that are going into the surface or into the volume. Okay. And so if you take the total net effect, and so you sum up all of the contributions for the entire surface, and assuming this vector field F is mass conserving, which we'll talk about that in a second when we talk about the other side of the divergence theorem. Assuming that F is conserving, then all of the contributions going out is going to be the same as all the contributions going in, and so they're all going to perfectly cancel out each other to give you zero. Okay. Okay. And so the parts that are going out and the parts that are going in are going to cancel each other out. And so this kind of revelation here kind of should shed some new light on how we interpret this. Okay. And so the surface integral for divergence theorem, I'll go ahead and leave it here just for a second. I'll talk about it first, something about it. The surface integral for divergence theorem is actually a special surface integral in that it's on a closed surface, right? It's not on an open surface, it's on a closed one. Okay. And so what that side represents is the total amount of flux, the net amount of flux, going in and out of a region. So this is the total net into okay. And this is where it kind of takes on kind of the physical definition. And so if your vector field F represents some conserved quantity, whether it be mass, whether it be momentum, whether it be energy, whether it be angular momentum in some cases, okay, there's a lot of conserved quantities in applied physics. If F is some conserved quantity, then this surface integral here will be 0 for a closed surface. I apologize, got a little bit messy, but I wanted to make sure that you can see the surface integral and have these notes. Okay. And so for those of you who have taken fluid mechanics or took it last semester, this should remind you very strongly of the Reynolds transport theorem. Right? So the Reynolds transport theorem is basically a statement of this exact same thing. Right, any questions on this here? Yeah.
So can the flux ever be negative?
It can, yes. And so a negative flux usually is for cases when the quantity is going into the dome.
Oh, so inwards is negative?
Yes.
Okay.
Yeah, it all comes to the dot product. So when F and N are aligned together, so you have stuff going out, then it's positive. But when F and N are going opposite directions, then it becomes negative.
Okay.
Okay, all right, so that's one side of the divergence theorem. I think it's the more interesting side. Let's look at the other side. So I'm gonna draw it down here. And so the other side of divergence theorem is our triple integral. It's the triple integral of the divergence of F. Okay. So the way to interpret this side is that this represents basically a density. So it represents the density of the quantity F in a fixed region of space. And so just like the surface integral, and so by the divergence theorem, we know that this triple integral is equal to the surface integral. If F is a conserved quantity and there's nothing being added to it, so there's no spontaneous, there's no creation of mass from nothing, then this triple integral will also be 0 for a conserved quantity. You might think, that's boring, right? So we went through, basically the entire lecture today talking about divergence theorem, and all we get is that it's all equal to 0. Like that's, it feels like we just wasted everyone's time. The interesting things happen when F is not a conserved quantity. And so when F is not a conserved quantity, then what you can have is either an accumulation or a depletion of F within the region B. So let me just give you some very, very simple examples. So let's say we have a spherical region. And then let's say our vector field F, okay, it's designed in a way where it only goes in. Let's say that we have our vector field F. If you took the divergence of F, within this region here, you're going to get something that's non-zero because we have basically all the arrows of F are kind of converging to the same point. Okay, and so in a sense, in one way that you can say this or think of this is that at the point where they all converge, F is not being conserved. Okay. And so in this case, we have an accumulation of F within our region. And so this would be something, if you were to talk about this in fluid mechanics terms, this would be like a sink. Okay. I'm not sure. I think not every fluids instructor goes over potential flow, but this would be an example of a sink. And it gets that name because, if you think about a sink in your faucet, right, you have, water that's coming in and then it flows down that drain. Okay. And then you can have the opposite as well. So if you have a situation where all the vector lines are pointing out, then that would be a source, because then you have basically mass or fluid that's being produced at a given point, and then all has to radiate out. Okay. And so there are situations, depending on how you draw your domain, and depending on how you kind of interpret your vector field, where you can have singularities like this, where F is not conserved. Okay. And those are cases where the divergence theorem is interesting. Okay. And so one way to kind of state it in plain words, another way to state the divergence theorem is the accumulation or depletion a quantity F is equal to the net inflow or outflow across the boundaries. This is simplified divergence. All right, any final questions on this? Okay, all right, so that's all we got time for. So thank you guys for coming today. Once again, I want to say, hope you guys have a wonderful spring break. It's not, I know the weather is not really conducive to it, but if you are traveling this spring break, please stay safe. Even if you're not traveling this spring break, please stay safe. It's very wet, it's very rainy out there. People are driving like crazy because you know how it is in Southern California. We have no idea how to live with the rain, so people don't know how to drive out here. So And so, if you're driving on the freeways or anything, please stay safe, because one thing I want to see here is I want to see everyone back here on Tuesday after the spring break. So, okay, so have a great spring break, rest up, because when we come back here, we're gonna pick up kind of where we. All right, so thank you guys. I'll see you after spring break. Oh, if you haven't picked up your exam yet or your cheat sheet, it's here as well. So. Yes, yeah. So they start at 1 o'clock. Normally they go until 3, but I know there's quite a few people coming to walk, so I'll probably extend it. Yeah. Well, it's gonna be CS 526. Okay. Thank you. Yeah. Any final questions before I wrap up the call? Okay, all right, I'll see you after spring break. Oh, sorry, you say something? Oh, no.